Hey everyone, and welcome to the internet. What we're going to be doing in today's lesson is having a look at polymers. So hopefully by the end of this lesson you'll be able to describe what polymers are and explain their structure and the bonding that we find within them. To start us off, we've got 3 questions based around our previous lesson, so have a go at answering those 3 questions in your books for me. Let's check those answers. So question 1, a covalent bond is a shared pair of electrons. Give yourself a tick if you got that. Question 2, you were drawing the structure of methane. So you've got your carbon in the middle, and carbon has 4 electrons in the outer shell, which I've represented with the crosses in this case. And each of those is shared with a hydrogen. So we've got 4 hydrogens, and hydrogen has a single electron, which should be their dots. So if you use dots for your carbon, you need to use crosses for your hydrogens. If you got that, give yourself a mark. And then our carbon dioxide is a gas at room temperature because carbon dioxide is a simple molecule with weak intermolecular forces, 1 mark, which are easily overcome, so it's a gas, 2nd mark. Add it up and give yourself a score out of 4. What we've got here then are 3 sentences about polymers. Now there are 4 words at the bottom that will make up those blank spaces. So see if you can start off just by writing down those 4 sentences and filling in the words from the bottom box in the right places. Now, a polymer is actually a long chain of molecules joined together. So it's made from a certain type of molecule called a monomer. Now, mono means one, so it's a single unit, and these are a special type of chemical called alkenes. So a polymer is made from many alkene monomers joining together. Now, that sentence there is really important to learn because quite often when you're asked about what a polymer is, that first sentence there could very well get you a couple of marks. So, many alkene monomers joining together is our first bit. In order to allow those alkene monomers to join together, we need two very special conditions. First one is a high pressure, and the second is a catalyst. So those give it the right conditions for those alkene monomers to join together in this long chain. And what we're doing is, if you imagine we've got these individual units and then we're just sticking lots of them onto each other. So we're joining them together in a really nice long chain. And we refer to that type of reaction as an addition polymerization. So addition because we're adding them all on there, polymerization because we're making a long chain of them. So give yourself a mark out of 4 for those words. Any you didn't get, make sure you've written in the correct answer. What we need to know first of all then about our polymers is how to name them. And the good news is naming them is dead easy. We start off with the name of our monomer, so the individual unit. And if we're asked to write the name of the polymer, all we do is write the word poly and then the name of the monomer in brackets. If they give us the name of the polymer and ask us to name what monomer it's made from, all you do is you lose the word poly, lose the brackets, and just write down the bit that was in the brackets. So for example, we've got ethene is the monomer, and that makes the polymer polyethene. So we wrote the word poly and shoved ethene in brackets. For propene as the monomer, it becomes polypropene. So we've got a really quick check in the orange box in the bottom left there. That's our reminder as to how to do this. So make sure you stick that bit into a nice colourful box, highlight it, do something to make it stand out so you remember those really simple ways to be able to name any monomer or any polymer. Okay, let's see if you can put that into practice then. 2 questions on the screen, have a go at answering those in your books. Hopefully for question 1 we wrote down polystyrene, and for question 2 chloroethene. Give yourself a mark for each one you got right. So we know how they're made, we know how to name them, The next thing we need to be able to do is to draw the displayed formula, either for the polymer when we're given the monomers, or for the monomer when we're given the polymer. So what I've given you at the top, on the left hand side is the monomer, and on the right hand side is the polymer of that same unit. So what we can see, if we look at the picture on the left first of all, that's our monomer. And it's an alkene because we've got a double bond between those carbons there. Now, when that becomes a polymer, what we do is we redraw the 2 carbons and the 4 hydrogens, but we only join the carbons by a single bond in the middle. So what we've got are hydrogens still joined onto the carbons and the 2 carbons joined by a single bond. We then stick the little arms coming out the side from each carbon, and we put brackets around the whole thing and put little n in the bottom right, and that little n just stands for any number. So because it's a repeating unit that we're joining end to end, then the n just means it could be any number of those molecules. If we were given the polymer, the picture on the right, and asked to draw the monomer, all we do is the reverse. We're going to copy the bit in brackets, but without the 2 little arms sticking out the side, and putting the double bond back in the middle. So again, the bit in the orange box, that's our kind of quick guide, if you like, on how to get this right. So highlight it, stick it in a box, make it stand out so you know to learn that. And I'd suggest you also do the diagrams at the top as a reminder of how to do this. So I'll leave this up for another minute or so just to give you a chance to copy those bits down. Your turn to put it into practice then. 2 questions for you to have a go at answering. Let's double check our answers then. So for the first one, we were given the monomer and we had to draw the polymer. So we redraw it as it is, just without the double bond, stick the arms out the side, put it in brackets, little n in the bottom right. If you got that, give yourself a tick. Then for number 2, we need to draw the displayed formula for the monomer when we're given the polymer. So what we do is we draw the bit that was in brackets, but no arm sticking out the side, and we put the double bond back in the middle. Again, give yourself a tick if you got that right. When it comes to polymers, we can actually divide them up into 2 types. So we either have thermosoftening polymers, and that's the picture at the top there, or we have thermosetting polymers, like the one at the bottom. Now, what I'd like you to do is, looking at those 2 diagrams, I want you to explain the difference in structure between those 2 polymers. And I'd suggest before you get stuck into the explanation, you do a quick sketch of what each of them looks like, just as a reminder. So I'll give you a couple of minutes to do your sketches and explain the difference in structure between them. Hopefully what we noticed is that the thermosoftening polymer has no crosslinks. So realistically what we've got there are the individual lines, those are the polymer chains. And what happens is they're weakly attracted to each other. So they have these weak intermolecular forces. Whereas the thermosetting polymer does have these crosslinks, and those crosslinks are strong bonds. So they hold the polymer chains in a more rigid structure. Now the crosslinks themselves are covalent bonds, and they're holding those individual polymer molecules together. Now because we've got these covalent bonds holding the polymer molecules together, we'd need quite a lot of energy to actually separate them by breaking those covalent bonds. Whereas the non-cross-linked polymers, these are easy to separate because those intermolecular forces between the individual polymer chains are actually very weak, so they're easily overcome. And this gives us one of those key properties of our different plastics, in the fact that those that do have the crosslinks have a more rigid structure, so they hold their shape, they're harder to actually change the shape of. Whereas those that don't have the crosslinks, the thermo-softening ones, they're really easy to change the shape and stretch. So to give you an example of different bits, if we think about the polymers that do have the crosslinks there, that would be like the plastic trays you have in school or the stools you sit on, because they're quite rigid, it's hard to change the shape of them. Whereas the non-cross-linked polymers, that would be like the plastics we use in carrier bags, because if you pull on them, what you're really doing is stretching them, because the weak intermolecular forces are easily overcome between the chains, and those chains just slide over each other. Make sure you've got the 2 sentences written down. I'll leave it up for another minute in case you still need more time. Last thing for today then is a 6-mark question for you to have a go at. So polypropylene is used to make sandwich boxes. Look at Anna's sandwich box, it contains sandwiches for her lunch. And just in case you didn't know what a lunchbox with sandwiches looks like, there's your picture. One of the properties of polypropylene is that it is flexible. Explain why polypropylene is flexible and suggest, with reasons, 2 other properties needed by polypropylene to be suitable for making a sandwich box. So as always with a 6-mark question, remember we've got 2 different things that we need to do here. Firstly, explain why polypropylene is flexible, and secondly, suggest with reasons 2 other properties needed for it to be suitable for making a sandwich box. Now, 6-mark question, I would always recommend you use about 6 minutes to answer it, because it's usually about a mark a minute on your exam papers. So I'll leave this up for 6 minutes today, but as always, if you really want it up for a bit longer, you can hit pause and take as long as you need.